Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Here is the generated essay. The year 1995 witnessed the publication of a landmark achievement in number theory, a work that cemented Andrew John Wiles' name in the annals of mathematical history. Modular, elliptic, curves and Fermat's last theorem. This paper, published in the prestigious Annals of Mathematics, provided a definitive proof of Fermat's last theorem, a problem that had remained unsolved for over 3.5 centuries. This essay undertakes a detailed, section-by-section evaluation of Wiles' 1995 publication, examining its central claims, analysing its methodology, and contextualising its arguments within the broader mathematical landscape, maintaining a focus on the internal logic and specific assertions made within the work itself. Section 1: Introduction and Statement of the Problem. The introductory sections of Wiles' paper commence by establishing the profound link between modular elliptic curves and Fermat's last theorem. It is posited that demonstrating the modularity of all elliptic curves over the rational numbers would inherently prove Fermat's last theorem. This connection arises from the work of Gerhard Frey, Jean-Pierre Sed, and Ken Ribet, who showed that if Fermat's last theorem were false, then there would exist an elliptic curve that is not modular, a Sogel-Frey curve. Hence, proving the modularity of all elliptic curves would preclude the existence of such Frey curves, thus validating Fermat's last theorem. Wiles' introduction clearly articulates the strategy, setting the stage for the complex arguments that follow. The initial claim, therefore, is that the modularity conjecture implies Fermat's last theorem. This claim is not itself proven by Wiles. It is asserted as a consequence of the collective works cited. The substance of the paper hinges on establishing the modularity conjecture in the context necessary to indirectly approach the theorem in question. This section's success resides in its concise presentation of the problem and the strategy employed to address. Section 2: Elliptic, curves and modular forms. This section delves into the essential background concepts of elliptic curves and modular forms, laying the groundwork for the more intricate arguments that follow. An elliptic curve is defined as a non-singular cubic curve given by a Weierstrass equation. Wiles then proceeds to illuminate the properties of elliptic curves over the rational numbers, including their group structure and the L functions associated with them. Crucially, he underscores the concept of modularity, which asserts that the L function of an elliptic curve is equal to the L function of a modular form. A modular form, in turn, is a holomorphic function on the upper half-plane that satisfies certain transformation properties under the action of a congruence subgroup of the modular group. Wiles rigorously defines these concepts, establishing a solid foundation for subsequent arguments. The key claim in this section is the accurate and precise definition of elliptic curves and modular forms, and the assertion they are intrinsically related through their associated L functions. The rigor of these definitions is paramount, as they form the toolkit with which the proof will be constructed. Lack of clarity at this stage would undermine the entire endeavour. The careful exposition of these foundational elements is a testament to Wiles' meticulous approach. Section 3: Galois representations. Central to Wiles' proof is the theory of Galois representations. Given an elliptic curve E over the rational numbers, one can associate to it a Galois representation, which is a homomorphism from the Galois group of the rational numbers to a general linear group over a finite field. These Galois representations encode arithmetic information about the elliptic curve. Wiles demonstrates how the modularity of an elliptic curve can be detected by studying the properties of its associated Galois representation. Specifically, he shows that if a Galois representation associated with an elliptic curve arises from a modular form, then the elliptic curve itself is modular. The claim here lies in a precise construction, linking elliptic curves to modular forms through Galois representations. It is in exploring the properties of these representations, such as their reducibility and deformation, that Wiles builds a pathway toward proving their modularity. This section is critical because it bridges the gap between the geometric world of elliptic curves and the analytic world of modular forms via the algebraic structure of Galois representations. Section 4, Hecke algebras and the main conjecture. This section concerns itself with Hecke algebras, which are algebras of operators acting on modular forms. Wiles introduces the crucial concept of a Hecke ring, denoted by T, and demonstrates its properties. A Hecke ring is a commutative algebra generated by Hecke operators, which are linear operators, and preserve the space of modular forms. Wiles then frames the critical main conjecture, suggesting a deep relationship between the Hecke ring T and certain deformation rings R. The main conjecture can be stated as an isomorphism between a Hecke ring and a properly chosen deformation ring. The specific form of the main conjecture relevant to Wiles' proof relates the arithmetic properties of modular forms to the deformation theory of Galois representations. This conjecture, while not explicitly proven within Wiles' paper itself, serves as a crucial stepping stone in the overall argument. The claim here relies on the well-established properties of Hecke algebras and their interaction with modular forms. The significance of this section lies in its introduction of the crucial bridge connecting modular forms and Galois representations. This bridge ultimately allows Wiles to argue for the modularity of elliptic curves. Section 5, Ring theoretic criteria for modularity. Wiles develops sophisticated ring-theoretic criteria that allow him to deduce the modularity of an elliptic curve based on the properties of its associated Galois representation. He establishes a series of intricate lemmas and theorems that provide sufficient conditions for a Galois representation to arise from a modular form. These theorems are formulated in terms of the deformation rings R and the Hecke rings T. Wiles shows that if certain conditions are satisfied, then the deformation ring R is isomorphic to the Hecke ring T. This isomorphism is a cornerstone of the proof, as it allows him to transfer information between the algebraic world of Galois representations and the analytic world of modular forms. The core claims in this section are the theorems establishing the isomorphism between the deformation rings and Hecke rings under specific conditions. These theorems represent a significant contribution to the theory of modular forms and Galois representations. The power of these criteria lies in their ability to transform the problem of proving modularity into a problem of verifying specific ring-theoretic conditions. Section 6, Deformations of Galois representations. This section delves deeper into the deformation theory of Galois representations. Wiles explores the concept of deformations, which are essentially families of Galois representations that are close to a given representation in some sense. He provides a detailed analysis of the deformation rings, parameterize these deformations and establishes various properties of these rings. The key claim centers on the control of these deformations. Wiles demonstrates that under suitable conditions, the deformation rings are relatively small or well-behaved, which is crucial for establishing the isomorphism between the deformation rings and the Hecke rings. He specifically examines universal deformation rings which parameterize the entire collection of deformations satisfying certain criteria. The universality of these deformations allows for a comprehensive study of their properties. This section is essential for controlling the complexity of the Galois representations and ensuring that they behave in a predictable. Section 7. The main theorem and its proof. The heart of Wiles' paper lies in the statement and proof of the main theorem, which asserts that a large class of elliptic curves is modular. Specifically, Wiles proves that all semistable elliptic curves over the rational numbers are modular. This result is sufficient to prove Fermat's last theorem, since the hypothetical for a curve associated with a counterexample to Fermat's last theorem would be semistable. The proof of the main theorem is a culmination of all the previous arguments. Wiles combines the ring-theoretic criteria, the deformation theory of Galois representations, and the properties of Hecke algebras to establish the desired modularity result. He shows that for semistable elliptic curves, The conditions required for the isomorphism between the deformation ring R and the Heck ring T are indeed satisfied. This isomorphism then implies that the elliptic curve is modular. The central claim of this section is the modularity of semistable elliptic curves. The proof involves a complex interplay of algebraic and analytic techniques and represents a remarkable achievement in number theory. Section 8. Application to Fermat's last theorem. Having proven the modularity of semistable elliptic curves, Wiles proceeds to demonstrate how this result implies Fermat's last theorem. He recalls the work of Ray, Serre and Ribet, who had shown that if Fermat's last theorem were false, then there would exist a semistable elliptic curve that is not modular. Since Wiles has proven that all semistable elliptic curves are modular, it follows that Fermat's last theorem must be true. The argument is a reductio ad absurdum. Assume Fermat's last theorem is false. Derive a contradiction the existence of a non-modular semistable elliptic curve. Therefore, the initial assumption must be false. The beauty of this section lies in its concise and elegant application of the main theorem to resolve a problem that had confounded mathematicians for centuries. It serves as a powerful demonstration of the interconnectedness of different areas of mathematics. The claim here is not a new theorem, but rather the logical consequence of the main theorem and prior results. Finally delivering the proof to Fermat's last theorem, Wiles' paper therefore provides a complete and rigorous proof of Fermat's last theorem, a feat of unparalleled intellectual accomplishment. Section 9. Errors and corrections. Despite the groundbreaking nature of Wiles' work, the initial published version contained a gap in one of the arguments. This gap was subsequently filled in collaboration with Richard Taylor and published in a separate paper, also in 1995, titled Ring Theoretic Properties of Certain Heck Algebras. The error centered around a subtle point in the deformation theory of Galois representations. While the error was significant, it did not invalidate the overall strategy or the main conclusions of Wiles' paper. The corrected proof, which incorporates the results of the joint paper with Taylor, is now considered complete and definitive. This section acknowledges the initial imperfection, emphasizing that even in groundbreaking achievements, errors can occur. It points to the collaborative nature of mathematical research where errors are identified, addressed, and the correctness of results re-established. The claim here is the explicit acknowledgement of a past error and its subsequent resolution, highlighting the self-correcting nature of the mathematics discipline. The inclusion of this correction emphasizes the thoroughness and integrity of the mathematical process. Section 10. Subsequent developments and significance. Wiles' proof of Fermat's last theorem has had a profound impact on number theory and related fields. It has spurred a vast amount of research into modularity conjectures, Galois representations, and deformation theory. Subsequent work has extended Wiles' results to cover a broader class of elliptic curves. The full modularity theorem, which asserts that all elliptic curves over the rational numbers are modular, was eventually proven by Christopher Breuil, Brian Conrad, Fred Diamond, and Richard Taylor. The techniques developed by Wiles have also found applications in other areas of mathematics, such as algebraic geometry and representation theory. More generally, the study of modular forms and Galois representations remains a central theme in modern number theory, and Wiles' work continues to inspire and guide researchers in this area. The proof demonstrated a deep connection between elliptic curves and modular forms, sparking further investigation to uncover more hidden interrelations within mathematics. The claim here is the highlighting of the continuing significance of Wiles' proof to stimulating further research, as well as to highlighting the power and utility of the techniques that he developed. Section 11. The concept of modularity. The deeper dive. The concept of modularity, central to Wiles' work, warrants further examination. Modularity asserts that seemingly disparate objects, elliptic curves and modular forms, are fundamentally linked via their associated L functions. This link is not merely a superficial correspondence, it reveals a deep and underlying structural relationship. The modularity theorem provides a powerful tool for studying elliptic curves, allowing mathematicians to leverage the well-developed theory of modular forms to gain insights into the arithmetic properties of elliptic curves. The modularity correspondence manifests itself through the existence of modular parameterizations, which are maps from modular curves to elliptic curves. These parameterizations provide a geometric realization of the modularity relation, allowing one to visualize the connection between these two types of objects. The existence of these parameterizations highlights the interconnectedness of different areas of mathematics, bridging the gap between geometry and number theory. The claim here is the attempt to explore the concept of modularity not merely as a technical term, but a window to accessing a deeper interconnection in mathematics. Section 12. The role of Iwasawa theory. Iwasawa theory, a branch of number theory that studies the arithmetic of infinite towers of number fields, plays a subtle but important role in the proof of Fermat's last theorem. Although Iwasawa theory is not explicitly mentioned in Wiles' main paper, it provides a crucial framework for understanding the behavior of Galois representations and deformation rings. Specifically, Iwasawa theory helps to control the growth of Selma groups, which are arithmetic objects that measure the failure of the local global principle for elliptic curves. By using Iwasawa theoretic techniques, Wiles was able to establish bounds on the size of Selma groups, which in turn allowed him to prove the isomorphism between the deformation ring R and the Heck ring T. The claim is to highlight the critical role that Iwasawa theory plays in the proof of Fermat's last theorem by indirectly linking it to the control of growth of Selma groups. The inclusion of Iwasawa theory demonstrates the sophisticated tools from diverse areas of number theory used to address the Fermat's last theorem. Section 13. The significance of semistability. The restriction that Wiles' initial proof applied only to semistable elliptic curves might appear limiting. However, this restriction was crucial for technical reasons. Semistable elliptic curves are, in a sense, the simplest elliptic curves, and their Galois representations exhibit certain properties that make them more amenable to analysis. In particular, the Galois representations associated with semistable elliptic curves are easier to deform, which simplifies the problem of proving the isomorphism between the deformation ring R and the Heck ring T. Furthermore, the Frey curve associated with a counterexample to Fermat's last theorem is semistable, which is why proving the modularity of semistable elliptic curves was sufficient to resolve the problem. The eventual removal of the semistability condition by other mathematicians demonstrates the power of Wiles' initial breakthrough, which laid the foundation for a more general result. The claim here is the evaluation of the importance of the semistability condition towards simplifying the proofs. Section 14. The collaborative nature of mathematical discovery. The story of Wiles' proof of Fermat's last theorem underscores the collaborative nature of mathematical discovery. While Wiles' individual contribution was monumental, his work built upon the ideas and results of numerous other mathematicians. The connection between modular elliptic curves and Fermat's last theorem was first conjectured by Taniyama and Shimura, and subsequently refined by Weil. The crucial link between Fermat's last theorem and the modularity conjecture was established by Frey, Sen, and Ribet. Furthermore, Wiles' collaboration with Richard Taylor was essential for correcting the initial error in his proof. The history of Fermat's last theorem is a testament to the fact that mathematical progress is rarely a solitary endeavour. It shows that mathematicians build upon each other's work, contributing their own insights and expertise to solve problems that are often too complex for any single individual to tackle alone. The claim is to emphasize the collaborative nature of mathematics. Section 15. The enduring legacy of Fermat's last theorem. Despite its resolution in 1995, Fermat's last theorem continues to fascinate and inspire mathematicians. The theorem itself is deceptively simple to state, yet its proof requires a vast array of sophisticated mathematical tools. The journey to proving Fermat's last theorem has led to the development of new and powerful techniques in number theory, which have had a profound impact on the field. The theorem also serves as a reminder of the enduring power of mathematical curiosity and the human desire to understand the universe. The quest to prove Fermat's last theorem has captivated generations of mathematicians and has left an indelible mark on the history of mathematics, as it highlights the interconnectedness of different areas of mathematics. The claim is to highlight the continuing inspiration and enduring power Fermat's last theorem has on mathematicians. Conclusion: Andrew John Wiles' 1995 publication, Modular Elliptic Curves and Fermat's Last Theorem, represents a monumental achievement in number theory. Through a complex and intricate argument, Wiles successfully demonstrated the modularity of semistable elliptic curves, thereby proving Fermat's last theorem. While the initial version of the proof contained a gap, the corrected version, published in collaboration with Richard Taylor, is now considered complete and definitive. Wiles' work has had a profound impact on number theory and related fields, spurring a vast amount of research into modularity conjectures, Galois representations, and deformation theory. Beyond the specific result achieved, the proof provides a paradigm for linking seemingly disparate areas of mathematics and for applying sophisticated techniques to solve long-standing problems. The proof, though initially met with a minor setback, stands as a testament to ingenuity and the collaborative spirit that often prevails within the mathematical community, and is a towering achievement in the landscape of mathematical thought.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.